What's going on, basement hackers? Today we're going to get back into linking, but the tutorial we've been following seems to have been taken down. It was on uh, some weird website. The link I had doesn't seem to work anymore. I was thinking of jumping into a few other tutorials, just trying to search more for people showing end-to-end examples. We were going through all the nitty-gritty stuff near the end of the tutorial, but we're kind of at the point where we need to start working with it and trying to map to our, what is it, the QEMU, which I didn't get started, so let me just get that going, and then I'll show you my screen. Okay, let me show you that, and we can start looking at it and getting into some of it. Alright, so this guy, his description's not too long, and it would be good to just do an overview from somebody trying to show you a soup to nuts, the entire thing from end to end. So from zero to main, demystifying firmware linker scripts. So here's another post. Maybe we should go there first. Let's see. Bare metal rust. I don't really want to do anything with rust. Bare metal save from zero to main. Working on embedded systems, one quickly develops a quasi-religious respect for the axiom of embedded C programming. The entry point of thy program shall be named main. Thou shalt initialize thy static variables, else the machine shall set them to zero. Thou shalt implement the interrupts. Hard fault handler, chief among them, but also systic handler. Yeah. As an engineer, where those rules come from, and the wave towards cryptic startup files implemented in assembly. Oftentimes, those files are copy pasted from project to project. Seldom are they ever read, let alone modified. Throughout the Zero to Main series of posts, we demystify what happens when power is applied and when your main function is called. In this process, we'll learn how to bootstrap a C environment, implement a bootloader, relocate code, and more. So this is a lot of good stuff. Some of this will be interesting. And yeah, let's just go into this. Setting the stage. Well, most of the concepts of code presented in this series should work for all Cortex-M series microcontrollers. Our example targets will be this SAMD processor from Atmel. This is a Cortex-M0 Plus chip found on several affordable development boards. Specifically, we are using the Adafruit's Metro M0 Express as our dev board, a simple CMSys DAP adapter, which is like the Cortex-M layer. The Open OCD for programming. I'm guessing this is their programmer. In each case, we'll implement a simple blinking LED application. It is not particularly interesting in itself, but for the sake of completeness, we will find the code reproduced below. So all they do is they go through and they have a busy loop, and they toggle this, toggle just, they get the pins, they set the direction to output, and then I don't know why they do it every single time. You'd think that would be like a setup thing, but whatever, because they set it as out right here. But anyway, then they, where did they actually use the pin? Oh, that's a set output. Toggle they don't show here. Yeah, so they're just setting it as an output, and they're setting it low, and that's the set output. And the pin is the 17. And bool int, the port must be for port config, and this must be for this function here probably. So let's move on. Power on. So how did we get to main? All we can tell from the observation is that we applied power to the board and our code starts executing. There must be behavior intrinsic to the chip that defines how code is executed, and indeed there is. Digging into the ARM technical reference manual, this will be interesting to go into. I'm going to put it at the end. Which the underlying architectural manual for the Cortex M0 Plus. Is this for all of them, or is this it's V6. I know what we were doing is V7. V7E, I think. So we might look for the reference manual for V7E. We find some pseudo code that describes the reset behavior. So take reset. So this is probably the entry point that they would do. They put 32 zeros in the VTOR. Okay. So this is all pseudocode. So they're going to iterate over 12, from 0 to 12, and they're going to put the vector table. What are they doing here? Zeros. They don't really say what it is, but they're zeroing out, I think, the VTOR. Then they're going iterating over it. And whatever R is, they're setting it to a blank word. Oh, VTORs is like a variable that they're going to assign to the vector table, which is all zeroed out. Oh, this is the type, is what it's saying. It's a 32-bit thing in the vector table. Mode thread. So current thread is a little weird to read. Oh, you must be initialized by software. So LR APSR, like status register. What's the AP? It's flags, but this is interrupt port, I'm guessing, and there's like 0 through 5 bits, so 6 bits. So they clear exceptions, preemptive priority mask, they set to 0. Some of this looks like stuff that you would do for like for your RTOS. So they're doing a whole bunch of stuff here. In short, the chip does the following: resets the vector table to all zeros. So this is a word, and I think that's what they're doing here. I don't know if that's bits or words, but it sounds like. So they're resetting the vector table, disable interrupts, load the stack pointer to 0. Where was stack pointer? No, stack pointer. So this one, I don't see any other SPs. This is like wait for. This is like when you're like pausing, like waiting for a signal. I forget. It's like usually underscore WFE. Disable interrupts. Load the stack pointer with 0 and the PC counter with a 4, which would get. Why 4? Mystery solved. You'll say our main function must be at address 4. Let us check. It must be 4 because maybe the fault handler is at 0. First we dump out our binary to see what's at 0 and at 4. So 0 Or is that like ELF or something? So minimal, they look at the head of it. If I'm reading this correctly, our initial stack pointer is... Oh, yeah, the stack pointer is always at the beginning. You load the stack pointer and then go to the branch instruction. That usually will go to your startup code. So our initial stack pointer... So the stack's going to be located there. And our... Okay, yeah, so it's in little endian. I think that's little endian when you gotta flip them. So it's in 20 whatever, 2000 hex. And our start address pointer is C1. So this address here is C1. Let's dump our symbols to see which one is at which one's at C1. So looking at that, the reset handler's there. Oh, the one is a thing because it's a thumb instruction, and it's so you'll be like, that's why it's not C0. The one doesn't actually get used as the address. It just says, oh, this is a thumb instruction. It's gonna say that somewhere. That's odd. Our main function is found at 2AC. Okay. No symbol is at C1, but the reset's at C0. It turns out that the lowest bit of the PC is used to, yeah, that's what I was just saying, which is one of the 2 instruction sets supported by ARM processors. So reset, because you can't address anything on a like you can't address at something like that. So the reset handler is what we're looking for. For more details, check out this of the reference manual. We could jump to that real quick just to see. Is there a table of contents? A1. What did he say? A4111. A41. Supports the thumb instruction set, including a small number of 32. Let me make this bigger because you probably can't see that at all. It supports a thumb instruction set as including a small number of 32-bit instructions introduced in the Thumb 2 technologies. A 16-bit instruction. Yeah, so there's 16-bit instructions. Okay, I mean it's just telling like some technical details on why it's like that. Alright, writing a reset handler. Unfortunately, the reset handler is often an inscrutable mess of assembly code. See the NRF 52. What did I use NRF stuff for? I know I used it at work at some point. What did I use that for? Yeah, so here's their reset handler in their startup code for GCC. Oh, it's the Nordic chip. I did it for our outdoor products. Okay. So they're like loading in the beginning of the text section into the register. Remember, like, oh no, it's the end of the text section. Is like some of the we know from just looking at other linker stuff that people would do B and E as the prefix to like a thing, and the text section would be all the code. So this is the end of the code, which they probably are referencing the LMA, the load memory address. So they want to know the end of it because then it's pointing right at the beginning of probably where their data is. And then R2 is going to be probably the virtual memory address. And then they're going to load in where all the data that needs to be copied in at startup. Subtract. What do they do? Sub S. Subtract with I think S means to set the flags. ARM zone. Pretty sure that's what it is. Sub S. I could be totally wrong. Exception. Subtracts a value, and yeah, I'm pretty sure the S just means that you're going to set the flags register. But what is the third value? Is that where it puts the answer? It subtracts the 2 and puts the answer in. So PR is, or PCLR. Then it does a branch literal. So it's going to branch to here on equal. So if you subtract R3 and R3 and they're equal, then wait, what? Or maybe if they're wait, what? But it's going to jump to here, else it's going to fall through and it's going to do this loop. I bet you it's subtracting these two, and if they're the same, if there's no BSS, then it's going to skip this section probably. And so what it's doing is probably looping through this now, where it's going 4 bytes at a time probably, and then it's like copying them. I don't know. They're using like one of the registers, R1, R3 to R0. It's not worth it. We're not going to go through all this, but yeah, it's cool. It's not even that long actually. It only comes down to here. We could probably decode all that, because at this point it's the fall handlers and the memory. This is a memory interface handler, like I don't know. I'm gonna say it's something to do with memory. I don't remember. I don't know. But so it's probably just this is that. So we could actually decode their whole startup code. It wouldn't be too bad. But we know that they're going to want to... Oh, there's some comments here. So this part of the work... So they're actually looking... So startup clear BSS. So if you wanted to clear it all out... But at some point, they're going to go and they're going to jump to... What's NMI? Here's where the execute system in it... Well, getting off topic, so let's go back. So instead of going through this file line by line, let's see if we can write a minimal... reset handler from first principles. I mean, the most minimal, wouldn't it just be, well, you do need to do some stuff like BSS. You want to copy it into the variables in RAM. And then you would want to just branch to main, right? Instead of going through this file line. Alright, so here's ARM's technical reference manual. Mails are useful. So here's the M3. So on reset, well, this formatting sucks. This is all a comment. The NVIC they set enable interrupts. Sleep on exit. Then they wall one. WIF. I can't even remember. Isn't that where it like pauses, waiting for an event to happen? Here's another reset. Yeah, wait for interrupt. Okay, so unfortunately the reset handler is often inscrutable. We already read all that. Initialization variables. Any global static variables must be set up. This includes initializing the BSS variables to 0. Oh yeah, BSS is 0. What am I thinking? Like the data section is the one that gets copied. And copying initial values from ROM to RAM for non-constant variables. Set up stacks. Oh yeah, you have to set the stack pointer to the beginning of your stack, and stacks. If more than one stack is used, the other banked stack pointers must be initialized. Yeah, normally you make like a block of all the stack pointers. The current stack pointer can also be changed to process from main. I don't know what they mean by that. The current stack pointer can be also changed to process from main. And as well as any runtime. Optionally, make calls to C++ runtime init code to enable use of heap, floating point, and other features. Usually you'll see floating point stuff there. A lot of times with embedded stuff we won't even use a heap. This is normally done by an underscore main from the C++ libraries. So our reset handler is responsible for initializing static and global variables and starting our program. This mirrors what the C standard tells us. All objects with static storage duration shall be initialized, set to their initial values. Before program startup, the manner and timing of such initialization are otherwise unspecified. So section 5.1.2 execution environment. To practice this means that given the following snippet, so you're going to have two static variables, foo and a bar, one of them is initialized. A reset handler needs to make sure that the memory for foo is at 0 and bar is at 2. 2? You went 32s. Should it be 4? Oh, and the memory at bar is a 2. I was thinking the size, like the memory address. Oh, they're saying that initialize foo to 0 and initialize bar to 2. Okay, yeah. So we cannot just go and initialize each variable one by one. Instead, we rely on the compiler, initially the linker, to put all these variables in the same place so we can initialize them in one fell swoop. For static variables that must be zeroed, the linker gives us a BSS, and it looks like the start and end, or beginning and end, depending on who you're dealing with. So as start and end addresses, we can therefore do. So we're gonna just walk over this whole thing, and they're incrementing it here instead of up here, but that's fine. So they're gonna just wherever it points at set to 0, and then post increment, and then whenever it hits the end, then it's done. So it goes from the beginning to just before the end of BSS. That always is what confuses me, is when you say the end, is it the last byte or is it the byte after? And I'm just going to always get that wrong, and it's such a detail that matters because you'll do stuff badly. For static variables with an initial or with an init value, the linker gives us, so we have the etext, which is the end of the program memory. Well, it's not the program memory, it's the code, executable code, as the address the init values are stored at. So it's always one after for the end. The start is added. So the S data is as the address. So like here when they do S, it's the first pointer, like it's at where the end is always the byte after. So S data as the address of the static variables where they live at, and then the E data as the end of the static variable's memory. So we're going to go from etext, which is probably the LMA, like the load memory address, and we're going to walk all the way to eData, right? Is that what they do? Yeah, so they walk to eData. So they start at eText, which is the end of the code, the executable code, but it's the first byte of the data, and it's not start data though, because start data is like a virtual memory address, and it doesn't have to. It can be remapped differently. It's like weird. So yeah, this is the data pointer. Initial values pointer. Where's that? If there's nothing if there's no data, like it's already at the end, then they seems like that's like unnecessary though. On eText. So eText is the beginning of the data. This is where they live at. So if it's already pointing at that, then we just skip it. Else we walk the data pointer to the end of data, copying it in, incrementing the pointers each time. I would have put parentheses because no, because you can't, because then it would screw it up. Putting it together, we can write our reset handler as now here they add the zeroing in. Did we saw? Yeah, we saw the zero. They actually flopped the order this time, but that's fine. So they copy the values and then they zero out the data. We still need to start our program. That's achieved with a simple call to main. They also overwrite the default value for the NVM control B man W bit errata reference blah. Then they call main and then they wait forever. I prefer just looping main, but making this a reset, because why would you want your microcontroller just to hang? Well, never mind. Because you want to hang so that you can get interrupts and be interrupt driven from that on. So I'm wrong. You will note that we added two things: an infinite loop after main, so we do not run off into the weeds if the main function returns. Yeah, because normally main's going to wait on an interrupt and do that in an endless loop. So unless you're using like an RTOS, and then it's going to manage all that stuff for you and do that work. And it's going to have like an idle task and stuff like that. Like the idle task is going to be scheduled whenever there's nothing scheduled, and that's going to have to wait for interrupt. Workaround for chip bugs, which are best taken care of before our program starts. Sometimes these are wrapped in a sysint function called by reset handler before main. This is an approach. So this is a Nordic thing to fix a bug in the chip. That's funny. Okay, closing. All of the code used in this blog post is available on GitHub. See anything you'd like to change, submit a pull request, or merge request, pull requests, whatever. A more complex programs often require a more complicated reset handler. Yeah. For example, relocatable code must be copied over. If our program relies on libc, we must initialize it. Edit. Post written. Bootstrapping libc with new lib. That's interesting. Because I don't know much about how libc is structured. More complex memory layouts can add a few copy and zero loops. We'll cover all of them in future posts, but before that, we'll talk about how the magical memory region variables come about, how our reset handler's address ends up F4, and how to write a linker script in our next post. So that's this one, I think. Let's just open it. That's funny. It's the same article, just different URL. Alright, so let me actually put that one back. I'll leave that one there and just jump to this guy. So we read that one, now we're back here. So last time we talked about the bootstrapping a C environment on a micro using, before invoking our main function. One thing we took for granted was the fact that functions and data end up in the right place in our binary. So thinking about our reset handler, back when we were doing our linking, it was always going to like that crazy address, and I couldn't understand why. I still don't understand why. Let me see if I can pull up our code. I just want to look at it again just to see what it looked like. Nice, it already came up. Cool. So looking at it, there's this project here. It's a reset thing, and it loaded the stack pointer, and then it branched to the entry point, and then it would just keep doing that over and over. This is like them calling main, and this is like what it was doing with at the beginning of his binary, how it was loading them into memory or into the stack pointer register. It's a little weird, because this makes me even want to think it should be at 0 even more, because his was at 0 and it loaded a stack pointer, and then it called the reset vector, which this is supposed to really be the reset though. So this is really, so like, it's almost like his did this for free and shouldn't even be in here, but then we would need to know about the for free startup code that we're getting, and how are we getting that, because we're not telling it to link that in. So it has to be put in somehow into our binaries. I don't know if it's, well, we know that like the entry point, this should be the entry point, because we use the entry command, and it does like command line, then it goes entry point, then it goes start, then it goes address 0. So I don't know. All right, let's keep going with his, and maybe he'll give us shine some light on it. One thing that we took for granted was the fact that functions and data end up in the right place in our binary. Today we're going to dig into how that happens by learning about memory regions and linker scripts. You may remember the following things happening automagically. We use variables like ESBSS and SData, etc. To know where each of these sections was placed in Flash, and to define where some needed to go in RAM. Pointer to our reset handler was found at address 4 for the microcontroller to find. Sorry. While these things are true for many projects, they are held together by at best by convention, at worst by generations of copy-paste engineering. We'll find some micros have different memory maps. Some startup scripts, probably his was Nordic and ours is TI, and that's probably the main difference. So, yeah, that's probably how it's going to end up. But the guy that was writing, that we modeled our linker off of, he was doing it off of that other machine. So ours might not even apply properly then, if that's the case. But we'll have to learn. And at some point, we're going to dive into our machine and really go and understand what we're writing for. But we wanted to just get the background knowledge before we did that. We'll find some micros have different memory maps. Some startup scripts name those variables differently, and some programs have more or less segments. Since they are not standardized, those things need to be specified somewhere in our project. In the case of projects linked with a Unix LD-like tool, that somewhere is the linker script. Once again, we will use our simple minimal program available on GitHub. Let's see if he has any other. Let's just look at it again. Yeah, it's still the same. He hasn't made any changes that didn't make it back to his thread post. So he has some fault handlers here, and I'm wondering if, so a lot of times these they're weak references, and what that means is you'll like define the implementation, and it'll use yours over some default implementation. But they external all these symbols that are going to be in the linker script because they're going to reference them everywhere. This makes it so that they can make this memory mapped right to it. And so the void pointer for the stack goes to the end of the stack. It's going to work its way up the stack. Reset the function pointer for the reset handler goes right here. I should know NMI. I can't remember what it is, but yeah, it's another function pointer and another function pointer, and then they define them all here. For if they get a hard fault, they just hang forever. If they get this, is this a Stack Overflow? I can't remember. NMI. I'm gonna look it up now. It's annoying me. NMI handler non-maskable interrupt. Is that when you can enable and disable? I know I've learned about it at some point, but it's escaping me. So here's where he did the stuff we read before. Oh, this is exactly what he had before. So cool. This is all what we already have seen. So the only thing we haven't seen is this, and let's go through his tutorial and not skip ahead. So, like interrupt, is that the name of this thing, interrupt? Maybe I'll subscribe at some point. Yeah, I'll take that offline. This seems like a fairly well-polished site. Uh-oh. Did I lose it? He didn't make it go into a new tab. Alright, reindeer, let's get back to it. Alright, so where we're at. Brief primer on linking. Linking is the last stage in compiling. Yeah, we know that there is the preprocessor, there's the compile, the assemble, and the linking. It takes a number of compiled object files and merges them into a single program, filling in addresses so that everything is in the right place. Prior to linking, the compiler will have taken your source files one by one and compiled them into machine code. Yeah, that's the compile step. Yeah, and then you'll have like an assemble step. In the process, it leaves placeholders for addresses as one. In process, it leaves placeholders for addresses as it does not know where the code will end up within the broader structure of the program, and it knows nothing about symbols outside of the current file or compilation unit. And that's what the linker is going to do. It's going to link all those symbols. It's also going to look for any symbols not defined or double defined. The linker takes all of those object files and merges them together along with external dependencies like the C standard library into your program. To figure out which bits go where, the linker relies on a linker script, or scripts, a blueprint for your program. Lastly, all placeholders are replaced by addresses. Yeah. We can see this at play in our minimal program. Let's follow what happens to our main function in the minimal. So let's clone his project. Why do I suck at using GitHub? Oh, so I need to go to the main page to get, copy. See the vagrant. Actually, we'll go to up one and make one called, what's this guy's website called? What's it called? Zero to main. Even though it's going to be a double folder, but Really? All right. I don't know why that's so hard. Let's just do it from not inside the VM. That might be the issue. I bet you my network is not working, but it seemed like it downloaded it. So this is a folder that is shared between my host machine and my VM. So remember, our VM is a Ubuntu Bionic LTS machine that we created with Vagrant. So I'll just get rid of this guy. Alright, so now we got 0 to main. So you got some make files in here and stuff, and Rust and things. Let's go to minimal because that's what we're going through. Alright, excellent. And we can open that up in here just to help as well. So I'll close the other guys. Man, my machine. I hate my machine. Alright. So let's compile it. So just looking at it, he's doing just the compile step is what the -c does. So it'll spit out object files. It'll do the preprocessor compile and assembly, but it won't do the linking because of the -c. And then the -o just says to call the output file this and put it at this spot, which I'm not going to use that. And then here's the file he's compiling and any C flags. Then he uses nm to dump it. You could do object dump too. nm shows you some good stuff on the symbols. And then they do linker flags. They take the object file and any other object files, and then here's the output file, an elf file. And if you dump the symbols on that, they're getting something else. So we can't actually run this because he doesn't have all the flags that we're going to need. I mean, I could probably figure it out, but it's probably not worth the time to go sidetrack on that. So all he's pretty much saying is you can compile it into objects, then see what's in the object and see how it's at address 0, because to that it's just an arbitrary location. But when it gets linked with all the other stuff and all the other object files and C libraries and things, main will actually get put somewhere else when it gets realized. The linker has done its job, so we could dump that. It does not have the addresses yet, and we then link everything. We dump it. The linker has done its job, and our main symbol has been assigned an address. The linker often does a bit more than that. For example, it can generate debug information, garbage collect unused sections of code. Is that link time optimization? Oh, that's what they're about to say. Or run whole program optimizations, also known as link time optimization (LTO). You'll have like -f LTO, or I think it's -f. I don't know. For the sake of this conversation, we will not cover these topics. For more information on the linker, there's a great thread on Stack Overflow. Anatomy of a linker script. So a linker script contains 4 things: the memory layout, the sections definition. That's the sections we've been mostly concentrating on. That's when you'll take the input sections and map them to output sections. Options. Okay, we haven't seen those. I know the memory layout's where you're going to define like your flash and your RAM, and maybe your ROM and anything else. Or if you have like non-volatile memory that you use as like a file system or something like that. and symbols, variables to inject into the program at link time. Yeah, but I mean the symbols can be inside defined inside the sections as well. But okay. All right, so memory layout. In order to allocate program space, the linker needs to know how much memory is available, so, and at what addresses that memory exists. This is what the memory definition in the linker script is for. So they're going to put like the main address and the length of it. It's going to have a name, and then you can have optional attributes in parentheses, where the name is the name you want to assign this region. Names do not carry meaning, so you can feel free to use anything you want. You'll often find Flash and RAM as region names. The attributes are optional attributes of the region, like whether it's writable, readable, or executable. Flash memory is usually read and executable, while RAM is usually read, write, and executable. That's cool. So you can load something into RAM and execute it out of RAM. Yeah. Marking a region as non-writable does not magically make it write protected. These attributes are meant to describe the properties of the memory, not set it. And so that's just so the linker can error on it if you try to, I guess, do something. I'm not exactly sure. Origin is the start address of the memory region. Oh yeah. And length is the size in bytes, and that you can use like the notations like K, G, B, or not KGB, K, M, and G. You would never have G though. That would be huge. Oh, you might. The memory map for this SAMD one from Nordic chip can also, that we've got on our board, can be found in its data sheet in here. So it has 256 kilobytes, and its SRAM, its static RAM, is starting address is at that 2 million address, and it has 32 kilobytes KB of RAM. So they're calling it ROM and RAM here, and this should match 52K. Let's just confirm that for the programmer calculator hex. Actually, yeah. 4, 1, 2, 3, 4, and that's 262, which is 256, but in pages. And because how does that work? It goes 128. Like, well, you'd have to know the page size. So if you did 4, and then you did this divided by, yeah, it's 1024. So it's 256 1K blocks. And the same thing is going to go for this 8,000 hex. You're going to have 32 of them. So times 32, and now you're going to have this, which is 8,000 hex. So that always like throws me off, but it's like, yeah, you buy like a 1 gig hard drive, it's really bigger than that. I do wonder why they chose 2 million for this. I mean, yeah, it separates a lot. It leaves a lot of room if you want to have different size chips in the family or across all your products. Or across, I know a lot of the chips do that though, is they choose this address. I'm guessing it's because it has 1 bit at the very far left, and then maybe the top other bits might be used for something special in the long run, and they know it's really large. I don't know. Section definitions. So now we're going to define the different sections. So code and data are bucketed into sections, which are contiguous areas of memory. There are no hard rules about how many sections you should have and what they should be, but you typically want to put symbols in the same section if they should be in the same region of memory, or they need to be initialized together. Correct. Yeah, you want, so you can get optimization. And then if there's certain regions of memory that are going to have security and stuff, then you would probably define them separately. But in our previous post, we learned about two types of symbols that are initialized in bulk. Initialized static variables, which must be copied from flash, and uninitialized ones, which must be zeroed out. Our linker script concerns itself with two more things: code and constant data, which can live in read-only memory, flash. Reserved sections of RAM, like the stack or a heap. By convention, we name those sections as follows. So .text for the code and constants. Right. I was thinking constants was in .data, but no, that's for variables that have initial values. The constants are in .text. Okay. BSS for the uninitialized data, stack for our stack, and data for our initialized data. I don't know why they put them in that order. I would put stack last, but the ELF spec holds a full list. Ooh, let's go look at that, because that's been executable and linking format. How long is this? This is not that long. Most of its indexes so far. This is where they talk about relocatable file, an executable file, shared object file. Now I know why he called it E-entry in his example. So where's it going to say the sections? Special sections. BSS, comment, data, data 1. It's a little weird. Debug, dynamic. Oh, cool, they're going to have descriptions. Sections hold initialized data that contribute to the program's memory image. Debug holds symbolic debugging. These contents are unspecified. All sections named with .debug are reserved for future use. Dynamic. Hash for hash table, line, note, read-only data. The section holds section names. .text, symbol table. So that's interesting. This would be another one to go through. I'm going to leave all these links open. Maybe we'll jump into them next time. So we just saw this ELF spec holds a full list. Your firmware will work just fine if you call them anything else, but your colleagues may be confused and some tools may fail in odd ways. The only constraint is that you may not call your section discard, which is a reserved word. We know that is so you can take an input section, throw it in the discard, and then you can wildcard easier. So here they define the ROM as read-only executable, starting at 0 at 40,000, which was like 256K in size, and then the RAM is read, write, and executable, and it starts at 2 million hex address, and it's 56K or something. I forget the exact size. The linker is perfectly happy to link our program with this, so it doesn't put anything in the output though. Probing the resulting ELF file with object dump, we see the following. Yeah, there's nothing. It has a format, little arm. So default to little Indian. No symbols, which the linker is able to make assumptions that it will allow it to link in symbols with little information, but it at least needs to know either what the entry point should be or what symbols to put in the text section. So the text section. So reviewing from last time, this is how you create an output section. It's not a symbol. This is an output section for text, and this is a block defining all the things that are going into it. There's nothing going into it, and then this is a region that they're defining it to be at. So this is going to put the text section at the beginning of ROM, but there's not going to be anything there. This defines the section name .text and adds it to the ROM. We now need to tell the linker what to put into that section. This is accomplished by listing all the sections from our input object file. So he could wildcard it, but he might spell them all out. But to find that, so he's going to dump out all of what our text section is. So we got all these text sections. So here's the object file. He does an object dump on it for our code that's been compiled but not linked. You can see all the different alignments. I wish you didn't have wrap on, but these are the sections we're going to want to put in there. We see that each of our symbol, so in it they have this pinmux get group from, so this is one function. This is another function. I can side by side it real quick. These. So we're gonna have port get group from GPIO pin. We might not reference it, but it might still be in the head defined. Yeah, so I showed that might have a trailing space. Yeah, it's not in here anywhere, but it's still in the object file. It's still compiled. Get config defaults. That's right here. Output level, set output levels right there. Toggle output level. Set output, which is our own function right here. And main, which is right here. Yeah, this was right here. So this is the only one that didn't get referenced, get group from GPIO pin. But we didn't need it. But it's probably like in this header, so that's why it showed up. But if you do link time optimization, it won't be linked in. So we see that, because nothing will reference it, we see that each of our symbol has a section. This is due to the fact that we compiled our firmware with the function sections and data sections flagged. That makes so much more sense now. I always couldn't understand those, but we had those in ours. If we look in, no, it wasn't this. Do we have it in here? We actually don't. It was in our other project. Thinking it's in. It's probably the ones in the GCC that have it, but now I know that those are important to have because it breaks that up. Did he say that when he said to compile? He didn't really say that, but yeah, he just said C flags. This is due to the fact that we compiled our firmware with function sections and data sections. So data sections are going to be these two right here. And those, if we go back to his code, well, these aren't going to be referenced anywhere here. Yeah, he has no static or global. This is a stack variable, stack variable. Yeah, everything's a stack variable. So these are variables that it must be defined in one of these two headers, or in code that we're linking from them into minimal. Okay, had we not included them, the compiler would have been free to merge several functions into a single .text section. Alright, cool. To put all of our functions in the .text section in our linker script, we use the following syntax. File, and then in parentheses with section. Oh my god. Where file name is the name of the input files whose symbols we want to include, and the section is the name of the input sections. So since we want all of the .text sections, then we do then we'll use the wildcards. So they didn't really talk about the vector. There's no vectors .vectors in here. Keep meant I'm trying to think if it's the one or the other. I think keep meant if some code defined it, then don't redefine it. No, it means don't be garbage collected. Note that the .vector input section, which contains functions we want to keep at the very start of our .text section. This is so that the reset handler is where the micro expects it to be. We'll talk more about the vector table in a future post. So this is literally the .vector. So if you're looking at his here, that's the section here. Oh, that makes way more sense now. This is literally saying we're now at the .vector, and then put that code here. And all of this code should just follow it as well. All this code will be in the vector section. When you compile this, it'll be in a .vector section. Why didn't we see it in? Oh, because this is in the startup code, so he only showed us the .o and not the startup code. Okay, cool. So this is referencing the startup code .vector section that's being defined right here. And this .text is all these, with the wildcard on the end, the star, is going to get every single one of these. And it's going to do them in order from top down. And star means every file that was in the command line, that passed in all of the input files. And this means all of the input files as well. But nothing will have the vector section except for this guy here. But that's interesting. If you want to put something at the beginning of memory, you would just have to put it in the .vector. You have to do one of these attributes. Now you wouldn't want to go in front of theirs, but you could like somehow put it after. Not sure why you would, but you could have a reason. Note that the .vector input section, which contains the function we want to keep at the very start of our .text. Yeah, so this will. So some of the syntax you should know is that it'll do all the .vector sections in every file, and then it'll do all the .text sections in every file. And the keep just says to not garbage collect it, which I still don't 100% understand what they mean by that. This is so that the reset handler is where the microcontroller expects it to be. We'll talk more about the vector table in a future post. Dumping our ELF file, we'll see all of the functions but no data. So let's see. So he linked it together and did an object dump on it. At address 0, there's the .text section, and in it there's minimal.c. Oh, because he probably is going to say, oh, and now we got to add stuff to the dot vector. Probably hasn't gotten there yet, so it hasn't pushed it down yet. So right now, the only thing that's in it is dot text stuff because there's no vector stuff. So that's why this is at the very beginning. And this is at the beginning because it's the first thing that's in here. It's this guy right here. So it's not even main, which is really funny because that'll, like, it would fall through all this code and then at some point, well, yeah, and then at some point hit main and then work. But this stuff could do a lot of bad stuff if there's no, like, proper reset that's going to branch to main at some point. So the BSS section, now let's take care of the BSS section. Remember, this is the section we put uninitialized static memory. And BSS must be reversed in the memory, reserved in the memory. But there is nothing to load as all the variables are initialized to 0. As such, this is what it should look like. So no load is the attribute they add to it. So it says not to try to load anything into it. And then but it says to take all the input sections and put them in there. And so, like, all of the input sections, which those sections are referenced by code within those object files, and possibly other object files too, if they're like global variables that are just not initialized. And so things are going to reference them, so they got to go somewhere. They're going to go there, but they're not going to be initialized to anything, except that our code is probably going to go zeroed out. And then common, we know, is that the weird thing, and there's like another common one, and it's just for people who made stuff complicated and more shit should have been standardized. You'll note that the BSS section also includes a common. So it's saying to get all the BSSs and then all the common. This is a special input section where the compiler puts global uninitialized variables that go beyond file scope. Right. Okay. Int foo goes there. So where do we get info? Where's info? Info? See, now I'm hungry. Info, yeah, goes there. And, well, static one does not. So the static would go in BSS. This allows the linker to merge multiple definitions into one symbol if they have the same name. How does that work? You merge them into one. Merge them into one. So allows them to merge them into one. You would want them to merge into one because two files referencing a global variable, you would want that to happen. But if I have two common sections, well, two things wouldn't want to declare it or define it. One thing would. So it will only show up in one common section. I don't know. We indicate that this section is not allowed, or not loaded with the no load property. This is the only section property used in the modern linker scripts. Really, it's the only one? Huh. No load? Alright. So the stack. So the stack won't load it also, which is, of course, what are you going to put in the stack? You're going to preload the stack? I mean, you had some type of, like, retention, like when you sleep your computer, if you were going to, like, sleep a micro and you had, like, non-volatile storage or, like, retention registers that are powered, but, and you wanted to just load a small stack back in, you could do something like that. Like your stack is still built into your RAM, which is faster, but you can like sync it to a persistent memory that's not NVM, but like not like a flash memory, but like a low power registers that you can reload it back into the faster flash at startup. That would be interesting, and then you wouldn't have no load. All right, so. We do the same thing with our stack memory since it is in the RAM and not loaded, as the stack symbols contains no symbols, we must explicitly reserve space for it by indicating its size. We also must align the stack on 8-byte boundaries per the ARM procedure call standards. In order to achieve these goals, we turn to our special variable. This is the line counter. Location counter, damn it. Also known as the location counter. The location counter tracks the current offset into the given memory region. As sections are added, the location counter increments accordingly. You can force alignment or gaps by setting the location counter forward. You may not set it backwards. The linker will throw an error if you try. We set the location counter with the align function to align the section, and use simple alignment and arithmetic to set the section's size. Yeah, so we align will use the current location counter and align to the next 8-byte boundary is what it's doing. Assigning that as a symbol assignment, then it is. I'm surprised they didn't make a variable here as top of stack or bottom or end of stack. Then they take the stack. Yeah, they should have made a variable right there that they assigned location counter to, and then they should have added the size, and then align in case the size was defined improperly, and then or was on like a weird size. Yeah, in case it wasn't an 8-byte boundary and it was like a 4-byte thing. I don't know. They realign it, and then they should have had like another variable or symbol defined. Only one more section to go. So the data section. Now this is one where they would want to copy stuff, so there's not going to be a no load. The .data section contains static variables which have an initialized value at boot. You will remember that our previous article that since RAM isn't persisted while power is off, those sections need to be loaded into flash. At boot, the reset handler copies the data from flash to RAM before the main function is called. So that was in our startup code, or his startup code. So that copies them all here. This zeroes out the BSS section. At boot, the reset handler copies all this data before calling main. To make this possible, every section in our linker script has two addresses: its load memory address and its virtual memory address. In a firmware context, the LMA is where your JTAG loader needs to place the section, and the VMA is where the section is found during execution. You can think of the LMA as the address at rest, and the VMA is the address during execution, i.e. when the device is on the and the program is running. Trying to just get a good context in my head. So that load memory address would never be RAM, because it's literally where you would load from. It would always be referencing it somewhere in flash, something like that. Or a virtual memory address could be mapped to RAM, to flash, I think, as well. And it's like the realized address. The syntax to specify the LMA and VMA is relatively straightforward. Every address is a two-part. In the AT, in our case, it looks like this. So they're saying put it in the load memory address, or this is the virtual memory address, and then the load memory address. I know there's a way to put the AT up here too after the colon. I'm wondering if this is just like future iterations of the syntax. Oh, they're going to show that right here. Yeah, you can do like this will do the LMA and this will do the VMA. So these are alternate syntax. Note that instead of appending a section to a memory region, oh yeah, because these are only for regions, where this you can put in a specific address there. Note that instead of appending to a section of memory region, you can also explicitly specify an address like so. I don't remember what origin is about. The origin of RAM. But you could just put an address here too, or put like a line, or put like the location counter, or just another symbol, or do an expression there. So that's interesting how they did that. That's pretty cool. So the @ says, put it here, but load it here. Like load to RAM, but write it to ROM. So like it'll be written to ROM and then loaded into RAM when it's at runtime. Where origin is simply a simple way to specify the start of a region. You can enter an address. So this is the same as the origin that's defined right here. Let's see. You can enter an address as a hex value as well. And we're done. Here's a complete linker script. So we're going to have all of our program memory output, so that it's going to be written to ROM. We're going to execute from there, and so it'll get read into the program PC and everything. And in our code, we're going to take all the vectors. We're going to first take the vector that doesn't have anything trailing and put that at the very beginning. So that's going to be this guy right here, because he's just dot vectors. He has nothing trailing him. And we're going to take all of those across all the files. Then we're going to take all the vectors. Actually, sorry, no. We're going to go to each file based on the order that they're in on the command line, and they're going to get the dot vectors, and then any other vectors are going to follow that from within that object file. And we're going to go object file by object file and append them one after another. Then at the very end of that, then we're going to go through every file and get all the .text sections. Then when that's all done, we're going to get all the read-only data and put it at the end. So this is all the constants. Then we're going to define an output section that is not going to be loaded at all. So it reserves space in RAM. And it's going to take all of the BSS sections out of all of the input files, which is all the object files being passed in. And then we're going to get all the common sections, which we now know are the global variables, where this would be static variables. Then the data, so this is all zeroed out memory, uninitialized I mean, which we would zero out though. Unless you didn't have to, if like the chip auto does it in hardware, or you just didn't even care. The .data, we're going to get all of them. That's going to be in ROM, which, he missed a space here, and that's going to irk me. But it's going to be reserved in RAM. And then our startup code is going to copy it from ROM to RAM. And then they're going to also have an output section for a stack